Today, we're diving into this incredible chemical battle that's happening literally everywhere, all around us and even inside of us every single second. It's this constant dance between two total opposites, acids and bases.
And think about this for a second. Have you ever wondered why a bee sting hurts so much, but something as simple as baking soda can make it feel better? It really seems like magic, right? But it's not. It's pure chemistry. And by the end of this, you are going to know exactly what's going on. All right, let's set the stage. To really get what's happening in this chemical showdown, we've got to meet our two main players. In one corner, you've got acids, and in the other, you've got bases. These two are like the fundamental opposing forces that define a huge chunk of the chemical world. So let's kick things off with acids. You've heard of them, for sure. Things like hydrochloric acid, or even the citric acid that makes lime juice so sour. But what actually makes an acid, well, an acid?
Okay, here's the secret. It all comes down to this. An acid is basically any compound that, when you dissolve it in water, releases hydrogen ions. You see them there? H+. These tiny little ions are the source of all of an acid's power. Take hydrochloric acid, HCl. The moment it hits water, boom, it splits apart, freeing up that all-important hydrogen ion.
But here's the thing. Not all acids are the same. You've got your strong acids, like that hydrochloric acid we just saw. When they hit water, they completely break apart. It's like a flood of H+ ions all at once. Then you've got weak acids, like the acetic acid you find in vinegar. They only release a fraction of their H+ ions. It's kind of like the difference between a fire hose and a leaky faucet.
And that power, well, it has some serious real-world consequences, especially with the strong ones. This symbol right here is a universal warning sign for a reason. They're corrosive. They can eat through metal, damage skin. You've got to handle them with some serious respect.
So, what are the dead giveaways for an acid? Well, first off, they have that famous sour taste. Just think of a lemon. We know they can be corrosive. Chemically, they do some really cool stuff, like reacting with certain metals to create hydrogen gas. Or, if they meet a carbonate, they'll bubble up and produce carbon dioxide. And of course, the classic test you might remember from science class. They turn blue litmus paper red.
And check this out. Here's one of those reactions in action. If you drop a strip of magnesium metal into hydrochloric acid, it fizzes and bubbles, creating magnesium chloride, which is a type of salt, and releasing a whole bunch of hydrogen gas. It's a perfect example of just how reactive these acids can be.
All right, we've got a handle on acids. Now it's time to introduce their polar opposite, the bases. If acids are all about giving away H+ ions, bases have a totally different job to do.
So what's a base? Simple. It's a compound that, when you dissolve it in water, increases the amount of hydroxide ions. That's OH-. Take sodium hydroxide, or NaOH. When it dissolves, it splits apart and releases that critical OH- ion. See how it's the perfect mirror image of what an acid does?
And you guessed it, just like acids, bases can be strong or weak. Strong bases, like sodium hydroxide, break apart completely in water, releasing a ton of those OH- ions. Weak bases, like an ammonia solution, only let go of a few. It's the exact same principle, just with a different key player.
Now, the properties of bases are totally different. They usually feel kind of slimy or soapy. Soap itself is a great example. Their most important chemical reaction, the one we're building up to, is how they react with acids. And in that litmus test, they do the exact opposite of acids. They turn red litmus paper blue.
Here are a couple of the heavy hitters in the world of bases. On the left, that's sodium hydroxide, and on the right, potassium hydroxide. These things are industrial powerhouses, used to make everything from soap and paper to cleaning products. Okay, so we've got these two powerful opposing forces. Acids are the H+ givers, bases are the OH- givers. But how do we actually measure that? How do we know if something is just a little bit acidic or dangerously acidic? We need a way to rank them.
That's the million-dollar question, isn't it? We need some kind of system, a yardstick, to measure this chemical power. And luckily for us, we've got one, and I bet you've heard of it.
Say hello to the pH scale. Think of it as chemistry's power meter. It's a super simple scale, usually going from 0 to 14, that tells us exactly how acidic or basic something is. The rule is easy. Low numbers are acidic, high numbers are basic.
Let's break it down real quick. Anything with a pH below 7 is an acid. Anything above 7 is a base. And right there in the middle, at 7, that's perfectly neutral. But here's the part that'll blow your mind. The pH scale isn't linear, it's logarithmic. That means a pH of 3 is 10 times more acidic than a pH of 4, and 100 times more acidic than a pH of 5. Every single step is a huge leap in power.
And now, we've arrived at the main event. This is the climax of our story. We've met the acids, we've met the bases. So what happens when these two sworn enemies finally come face to face? Well, you get a perfect balancing act.
This process has a name. It's called neutralization. It's what happens when those H+ ions from an acid get together with the OH- ions from a base. They meet, they pair up, and they completely cancel each other out. The powers of both the acid and the base just disappear. This right here, this is the heart of it all. The H+ ion and the OH- ion combine to form H2O. Just a simple, stable, perfectly neutral water molecule. It's the ultimate chemical peace treaty.
So when you look at the whole reaction, an acid plus a base will always give you two things, a salt and water. So in our example, hydrochloric acid and sodium hydroxide react, and what do they create? Sodium chloride, which you probably know as table salt, and water. The aggressive acid and the caustic base are gone, and all that's left is harmless salt and water. Pretty cool, right?
So, why should you care about any of this? Because this whole cosmic balancing act isn't just happening in a science lab. It's happening all around you, every single day, in ways that you might not even realize.
Let's go right back to that bee sting. A bee injects you with an acid, so you put on baking soda, which is a weak base, and you neutralize the acid. The pain goes away. Got an upset stomach from too much acid? You take an antacid, which is a base. It's the same idea. A wasp sting is the opposite. It's basic, so you treat it with a weak acid like vinegar. Even farmers do this, adding a base like lime to soil that's gotten too acidic for their crops. It's neutralization in action, everywhere.
So, from the acid in our stomachs to the dirt under our feet, this constant, invisible dance of neutralization is keeping our world in balance. It really makes you think, doesn't it? What other amazing, invisible forces of science are out there quietly shaping your life right now?